Hi, good afternoon. My name is Longfei Chen. Very glad to have the chance to present our work here. The title is User Behavior Analysis Towards Adaptive Guidance for Machine Operation Tasks. And this work is done with Yuichi Nakamura and Kazuaki Kondo from Kondo University. First, I will introduce the research background. In this study, we focus on human-machine interactions. Many types of machines commonly appear in our daily lives, and we want to learn the usage of them to help ordinary users to improve their working efficiency, especially for the first-time users and old people. In early times, we may refer to a text menu to learn to use such machines. Later, there are many manually made video tutorials, which help us easier understand the actual process through visual information. There are also some recent research works focused on automatically authoring guidance content, from task flow detection to task modeling, and offer help to users in an intelligent way. Here are some examples. As the left figure shows, they automatically extract important events in daily recorded experiences with gaze fixation, mostly as objects being interacted by hands. In actual guidance offering, the extracted information can be used to overlay to the user's workspace, such as pop up some notifications and reminders, or show short video clips of current step. Through this, the user can follow those instructions to finish the task correctly and efficiently. The biggest issue of such intelligent system is that they cannot adapt to each user with their desired ways. Different users may have very different demands during a task. Such as for beginners, they may need detailed step-by-step explanation. However, for experts, show every step to them would be annoying. Because they are already very familiar with the task, they may only need reminders on some crucial steps to reduce their mental workload for remembering large number of procedures. So, the task model should not limited to very few operation methods. For dealing with this issue, the user's skill level and personal habit are regarded as a key clues. In our previous work, we model the operation tasks through a two-step method, as shown in this figure. First, we build a baseline model with several standard experiences. Then, we align more and more beginners' experiences to the model. This can create an extensive representation of the task content. This model contains information from various behavior types of users that can be used for guidance generation. However, in this work, the identity of an expert or a beginner needs to be known beforehand, which is not possible for many actual applications, such as crowdsourcing. So in this work, we aim and study the behaviors of users from their skill learning process. We analyze the behavior changes of them with skill improving, from first-time users to near expert stage, in order to find the clues to identify their skills, operational difficulty, and also show their personal behavior habit. This can lead to the final goal of enhanced adaptivity of those intelligent guidance systems. Then I will present the detailed method. For our experiment environment, we choose a typical tabletop machine, the sewing machine, as a good example. The sewing task can compose of more than 10 steps with various operation patterns, such as push the button, seize the lever, rotate a dial, moving a slider. As a recording device, we use a head-mounted RGBD camera a static gaze tracker that pasted under the machine surface. By this, we're aiming at extract user behaviors from the vision and motion data. As in the video shows, the user wears a RGBD camera continuously capture the operations through egocentric vision. Our first step is to detect the task flow, which is the task procedures and their orders in an automatic way. So workflow detection is essential for task modeling and guidance generation. The task procedures are indicated by hotspots, which is the critical hand-machine interaction locations through the task. We detect the touches based on distance between hand and machine surface, then cluster them to hotspots. The interaction patterns and appear orders of hotspots can describe the operational procedures. Detailed information can be found in this paper below. Some previous works show the detailed relationship between user behaviors and their skills. In conceptual aspect, the skill learning process has been decomposed into 3 levels as the ideology of Shu-Ha Li, and 5 levels for the Dreyfus model. At the beginning stages, the learners obey the rules to formulate the concept of the task. At the middle stage, the graduate detach the rules by involving personal judgment. At the final stages, they no more rely on any fixed patterns. All the things are done naturally. In behavior aspects, they find that low-skilled users doing tasks much slower, have less stable operation motions, and the gaze often track the tools during a task because they are not familiar with them. Also, with deep neural network-based method and attention module, we find that the user skill is related to some certain actions, while not equally distributed among all the task process. Based on this observation, we design explicit behavior features by referring to the relationship among users' gaze, head, hand, and hotspot, as shown in this video. We extract the duration of each operation step, the distance between any 2 regions, also the motion features such as velocity, variance, and frequency. We also calculate the synergy of their movement by their correlation. We design another temporal feature called operational unit. This is inspired by the observations in common operation tasks, which describe the spatial temporal relationship between user's gaze, head, hand, and object. User starts from scanning the environment to build memory, then use gaze to lead the hand to approach the object. After hand has approached, the operation then begins. The operation unit can automatically segment each operation step into 3 sub-periods, as pure gazing, hand approaching, and operating. Some of those periods can be 0 among different operation steps. Here shows the different motion patterns of gaze and hand behaviors. When users search around, the gaze shows oscillation. When approaching the operation region, the distance between the gaze and hand to hotspot show monotonically decreasing. The gaze sometimes shift away to next step, while the hand is still operating the current region. This is called early shift. Then we show the experimental results. We recorded the sewing experience of 5 first-time users and their skill learning process for 2 tasks. We find that when their user skill improved, they have much shorter task execution time in all the periods. And the hand approaches target averagely faster. The gaze movement become more stable, and the head movement become more stable. From the feature value decreasing tendency, we can see that the users learn most of the knowledge within the initial 2 trials. Here examples show how gaze target changes. The blue line shows how gaze distant from the operation location. In early trials, the user often checked around. In middle trials, the familiarity of operation region increased with less searching around behaviors. In later trials, the gaze directly approached to the operation location and no more move. At the same time, the duration of this certain step is largely decreased when skill improving. Based on this kind of feature trend, we can calculate its correlation to user skills. We regarded the user skill is monotonic with task trial increasing, and calculated their correlation coefficient. From the result, task execution time is the most correlated to skill, followed by the head and the gaze movement. This means that we do the task much faster and do less check or search around when our skill is improved. We adopt similar way to find the correlation between behavior features and task procedure difficulty. The results show that the more dramatic the user gaze movement before and within operations, as the longer time for this step, the more difficulty this step is to the user. Then we compare the difference between gaze and head features. Gaze movement and head movement have sort of synergy relationship in operation tasks, but not always the same. We check this in our sewing tasks. The results show that the gaze and head movement are only weakly correlated in the horizontal direction. With user skill improving, the correlation becomes even weaker. Also, their interperson variations are similar. For indicate user skills, head movement performs better in our tasks. With the operation unit, we are able to look into the sub-periods of each operation to find the personal characteristics of user behavior patterns, such as user 1 operates slowly all time and checked around a lot before operation. User 2 and 4 operated fast without much check. User 3 searched a lot before operation, and user 5 confirmed a lot during operation. For those specific periods, it is considered appropriate to provide help to reduce their operation time. This shows how the personal behaviors can be checked with the above features. Finally, we check the gaze location differences. When the user skill is low, the current operating regions are often focused, and also the result regions. When the user skill is high, current operation regions are often ignored. They tend to look at the regions of next step. The result regions still draw a lot of attention. This shows how task familiarity influences the gaze behaviors. Here's our conclusion. First, we use our GBD camera and a fixed gaze tracker to sense user operation behaviors through egocentric vision. Then we designed multiple spatial temporal features to look into the user behavior in details. Finally, we check how those behaviors give us clues about the user skills, operation difficulties, and personal habits. All those information could be used to benefit future works, such as developing an adaptive user guidance. My presentation ends here. Thank you very much for listening.